Hello everyone, this is part 2 of inverse trig functions. So in our first part, we really dove into domain restrictions and when we can use inverses appropriately. And then on the second page of our notes here, we're going to get into solving some equations. Oftentimes, inverses are the way we solve these equations. So we're going to work through these. When we work through these problems, we want to pay special attention to the answer interval, right? They want us to give all answers over the interval 0 to 360 degrees. So first, that tells us that we're in degree mode here. And also it tells us that while our trig inverse function will only give us one answer, there can be more than one answer. So let's take a look. Here I have the sine of theta equals 1/2. So if I wanted to find theta, I could use inverses, right? I can take the angle whose sine is the sine of inverse sine on the right of 1/2. So theta equals angles whose sine is 1/2. So if I were to plug this into my calculator, it would tell me that my answer for this one, theta, is 30 degrees. That is true. However, this is not the only value on the unit circle with this sine value. The sine values are positive in the first and second quadrant. So if I have a sine of 1/2, theta could equal 30 in the first quadrant, or in the second quadrant, 150 degrees. So use caution if we're just using a calculator here. Our calculator follows our trig, our trig inverse domain restrictions very closely. So if you were to plug into our calculator the angle whose sine is 1/2, it will tell you 30 degrees, but it will not tell you its supplement, right? So we have to make sure we're expanding our work beyond just what our calculator tells us. Let's look at another one. Here we have 2 cosine of theta equals -√3. I'm going to solve this by working backwards. I'm going to take the cosine, divide both sides by 2 and say that the cosine of theta will be -√3 over 2. So sure, I can grab my calculator and plug this in, but this value here is familiar. This value is on our unit circle. Excuse me, and cosine is affiliated with the x coordinates on our unit circle. So if I have a negative value for cosine, it's going to be in the second and third quadrants. So my theta values are going to be, well, it's 150 degrees and 210 degrees. Right, a 30-degree reference angle in the second and third quadrants will lead us to a cosine value of -√3 over 2. All right, I'm going to say this again. We want to make sure we're going to be really careful to pay attention to where our answers must exist. All right, so just as a reminder there, we see from 0 to 2 pi. We're looking at example 3 here. They are asking us the cotangent of an angle equals -1. Where does that happen? So again, we certainly can use our inverse functions, but I really want to urge you towards using your unit circle. So in this particular case, the cotangent is negative. Cotangent is x over y. So if cotangent's x over y, I must have some value over a negative version of itself. Excuse me, not -1, right? That's the result here. Well, where do x and y values have the same coordinates on the unit circle? That happens at 45-degree angles. So we need to find the 45 or pi over 4 reference angles where cotangent is negative. Cotangent is positive in the first and the third quadrants. So a 45-degree or pi over 4 reference angle will exist in the second and fourth. So theta equals 3 pi over 4. That's in our second quadrant, and 7 pi over 4 in our fourth quadrant. Let's move on to number 4. Here we have secant. And generally speaking, I don't love secant, and if I can, I want to use its reciprocal function. So in this case, I am going to do just that. I'm going to say, where does cosine equal the reciprocal of 2? The reciprocal of 2 being -1/2. This should be a little bit more familiar, especially seeing that -1/2. That -1/2 shows up on our unit circle a few times. So if cosine is negative, that's happening on the left side of our graph in quadrants 2 and 3. If cosine is -1/2, that's closer to the x-axis than -1. So theta here is going to be a 60-degree reference angle, or 2 pi over 3 in the second quadrant, and 4 pi over 3 in the third quadrant. Couple more examples here where we can move on to number 5. So number 5 has a couple different ways we can solve. What I recognize here is the difference of perfect squares. So I would solve this through factoring and say sine theta -1 times sine theta +1 equals 0. And then I would figure out when does sine equal 1 and when does sine equal -1. So that's one way to solve it, and we'll finish that up in a moment. The other way we could do this, we could add 1 to both sides. So we could say we have sine squared theta equals 1. And then we could take the square root of both sides. So sine would equal plus or minus the square root of 1, which is sine theta equals 1 and sine theta equals -1. In both cases, we manipulate so we can evaluate, and we get sine theta equals plus or minus 1. I'm going to work over here on the left just to finish this problem up. So again, I'm looking for all values on our unit circle where sine is 1 or -1. Sine is our y-coordinate on the unit circle. So theta will only hit that higher low point once between 0 and 2 pi. It will happen at pi over 2, and it will happen at 3 pi over 2. Sine of theta equals 1 at pi over 2 and -1 at 3 pi over 2. So those are our two solutions. Last problem here, we have a tangent squared. We actually could solve this the same way we did the last one, right? Tangent theta minus √3 times tangent theta plus √3 equals 0. It's a little strange, but we can treat this as a difference of squares. And what we'll find is that we need to figure out when tangent theta equals √3 and when tangent theta equals -√3. So I'm working without a unit circle here, but I know that tangent is y over x. So if I have √3 over 2 divided by 1/2, that is going to end up with 2 √3 over 2, or just regular old √3. So where do I have a y value of √3 and an x value of 1/2? Well, that happens at pi over 3. So one of our answers here will be at pi over 3. That is happening when it's a 60-degree reference angle when tangent is positive. That will also happen in the third quadrant, so 4 pi over 3 is an additional answer. We can use the same reference angle to answer for these two solutions. We're going to end up with -√3 as our reference, as our tangent in the second and fourth quadrants when tangent is negative, and they will happen at 2 pi over 3 and 5 pi over 3. So for this last problem, we have 4 solutions. So the big idea with solving these problems, we are using inverse functions. However, inverses restrict our domain. Oftentimes, the problems we are solving will have a different domain than the restricted domain that we see with inverse trig functions. When we solve, we're trying to find all solutions over a given interval. Pay attention to that interval, pay attention to degrees and radians, make sure we know what mode we should be in. Good work, everyone.